morning, everyone, and thanks for attending the CSP seminar. So this week, we are very pleased to have Professor Ziv Goldfeld from Cornell ECE as our speaker. So he's an associate professor in the ECE department at Cornell. Prior to that, he was a postdoc at MIT, and he did his PhD from Ben Gurion University. And his research interests are in optimal transport, information theory, and statistics. And today he will tell us about robust and geometry-aware distribution estimation via optimal transport. So please join me in welcoming our speaker.
Thank you, everyone. Great to be here. First time for me visiting UMich, so I'm very excited about this. A wonderful place, and I'm looking forward to chatting with many of you later on today. I want to tell you a little bit about robust distribution estimation under a new attack model that combines both local and global corruptions, whereby local corruptions, I mean kind of small nudges or perturbations to the observed data points, like the type of attacks you see in adversarial machine learning, for example. Whereas global corruptions is your standard kind of corruption by outliers model, right? When I can grab an epsilon fraction of the mass and replace it with outliers at an arbitrary location. This is, as I mentioned, the standard model in robust statistics dating back to Huber's work in the late 60s. And the thing is that while both of these corruption models have been treated separately and minimax optimal methods have been devised, somehow there are highly non-trivial to combine with one another, because all the methods that we have, if you try to operate with them in a regime where both corruption modes can be present simultaneously, break down. Either completely break down or become suboptimal, and actually figuring out how to treat this unified setting involves some very interesting statistical and algorithmic challenges, and this is what we'll try to discuss today. But as my title suggests, I also want to be able to kind of do all of this in a geometry-aware manner. So let me maybe spend a couple of minutes talking about the role of geometry in machine learning. And I mean, we know that, modern ML is what's going on. 1 second. Yeah, there we go. Yeah, so we know that modern ML is powered by these rich and very rich multimodal data sets, and in order to process them, we typically embed individual data points, if it's images or language tokens, into high-dimensional feature spaces for further processing. And the thing is that these feature spaces oftentimes have some underlying geometry, with our features either concentrating on or around some low-dimensional manifolds within these high-dimensional ambient spaces. And if you have multiple points, maybe you're looking at something like that. And the more data points or modes or data sets that you bring into this picture, kind of a natural question arises, which is, given a metric on the data space that encodes its geometry, basically quantifying distances between data points with respect to that geometry, is there a natural way to lift this to a discrepancy measure between the full-blown data sets themselves in a way that respects that underlying geometry of the data space? Because this basic question of comparing data sets is in some shape or form basically a primitive of pretty much any machine learning task of interest that is out there. And so this is really the first idea that I want to set our sights on, getting this geometry-aware discrepancy measure between a data set that somehow inherits the geometry of the underlying space where the data itself resides. And this is where optimal transport theory comes into the picture, because the optimal transport approach is effectively to think of this underlying distance, and I'm using Euclidean distances here just for simplicity. Think of this distance as a cost function and learn a min cost matching between the two data sets with respect to this distance-based cost function, which in this simple example would probably look something like that. And I mean, aggregating this min cost matching in an appropriate way gives rise to the optimal transport problem, which is what I would like to describe next. So optimal transport is an old idea, dates back to the 18th century, to the work of the French mathematician Gaspard Monge, who originally actually came up with it in the context of some physical fortification problems that he was thinking about. And in our context, if I model my complex data sets as probability measures over some high-dimensional manifolds, then Monge optimal transport basically looks to minimize the expected cost associated with transporting or maybe reshaping one distribution into another with respect to this cost function C, where the minimization is over all what we call transport maps, which are basically deterministic functions from the X space where mu lives to the Y space where nu is supported, such that the map, again, rearranges this blue mass into the red shape over here. And this is called Monge optimal transport. I think the idea is pretty intuitive, rooted in physical principles, and in fact, under sufficient regularity and smoothness conditions, this is also a well-posed mathematical question with very deep connections to PDEs, to fluid dynamics, to Riemannian geometry. But The main issue with the smooth formulation, at least as far as we're concerned, is that it doesn't really play all that well with discrete distributions in the absence of smoothness, which is oftentimes what we care about in data-driven applications. And I mean, first and foremost, transport maps between discrete distributions need not even necessarily exist, right? Just think about transporting a point mass to anything that is not a point mass. I mean, deterministic functions do not allow you to split mass. So in this simple situation, you're looking at a set of transport maps that is empty, and the problem is not well defined. But even if you want to kind of, classify this as a pathology, which it is not, but let's say you want to do that and think about it as a completely from a completely pragmatic perspective, as an optimization problem that I just want to be able to code up on my computer and implement, then you also quickly realize that you're dealing with a horrible optimization problem here that is, first of all, highly non-convex in this decision variable T over here. And I mean, beyond that, I mean, even this optimization domain is not really closed under any reasonable topology you can put on functions. So despite the fact that Monge probably has the right idea in mind, in order to get something that works in data-driven settings, we do need a little bit more. And it really turns out that this inability to split mass is the core issue that we have to alleviate. And this was indeed addressed many years later by the award winner in economics, the Nobel Prize award winner in economics, the Russian mathematician Leonid Kantorovich, in his 1942 paper, where he basically fixed this inability to split mass using the notion of couplings. All right. So let me denote by the skep pi of mu and nu over here, the set of all couplings of my two marginal distributions mu and nu, where a coupling is just a joint probability measure on the product space that has mu and nu as the corresponding marginals. And I mean, in this context, you can really think of a coupling as a randomized transportation map, especially if you look at this factorization here at the bottom, because what it basically says is that you're now allowed to pick up the mass that mu assigns to a point x and distribute across different y locations according to this conditional y given x probability measures. So up to this extra flexibility, the problem is basically the same: minimize the expected transportation cost, but this time over all these randomized strategies as modeled by our couplings. And that's Kantorovich optimal transport. That's the standard way to set up the problem nowadays. And if there's any questions about the setup, I'm happy to address them. All right, so maybe a couple of comments about Kantorovich optimal transport. And first of all, you can observe, I mean, just take my word for it, that it subsumes Monge as a special case in problems where a deterministic function is indeed optimal. Kantorovich problem will be able to retrieve that, and the two values of Monge and Kantorovich will in fact coincide. Beyond that, you can observe that Kantorovich actually serves as an LP for linear program, LP relaxation of the Monge formulation, because now we're looking at an objective here that is linear in this phi, optimized over a constraint set, which is the set of couplings, which is basically a polytope that again is described by constraints that are linear in pi. So overall, you're looking at one big happy linear program, which is great from a computational standpoint, right? Because we have various algorithms for efficiently computing LPs. From an analysis standpoint, because LPs have so much structure, if it's stability, if it's duality, if it's various other properties that has kind of driven progress in optimal transport in the past couple of decades. But perhaps most importantly from our perspective, Kantorovich optimal transport gives rise to this desired geometry-aware discrepancy measure between data sets that we were targeting in the form of the Wasserstein metric. And this is actually one of the most interesting objects in optimal transport theory. In terms of the definition, Wasserstein metric is just your pth root of the Kantorovich optimal transport problem with a cost function that is your underlying distance raised to the power of p. I'm setting this up again over Euclidean spaces with Euclidean metrics just for simplicity of presentation. You can play this game with little to no modification over abstract metric spaces, let alone Riemannian manifolds. So I mean, let's stay with Euclidean, but keep in mind that this is much more flexible. And this object that we're getting out of this is called the Wasserstein metric for a good reason, because indeed it metrizes the space of probability measures with finite peak moments. This is what this little subscript p over here represents. And this metric space we're getting out of this, which is called the Wasserstein space, one of its unique characteristics is it actually entails a very rich geometry that is in many ways inherited from the geometry of the underlying space, just like we wanted. And let me try to give you some flavor of what I mean by that. And I mean, maybe a first order observation here is that the underlying geometry, the Euclidean geometry in our case, is just a teeny tiny piece of this Wasserstein space, because the Wasserstein metric between two Dirac measures just boils down to the base distance between the corresponding points, which is to say that, I mean, we call this, by the way, lifting the base metric to the Wasserstein space. And this basically says that, well, any idea that is there in Euclidean geometry also lives in the Wasserstein space. But things here go far beyond this simple first order observation, because through this lens, I can now take a lot of ideas that are natural to think about in Euclidean spaces, such as maybe straight lines or averages or projections or even optimization, and lift them to this abstract space of probability measures as well. Okay? Because for instance, in the Wasserstein space, you can ask not only how far two distributions are from one another, I mean, that's what the metric gives you, but you can also think about the shortest path between them whose length is this distance. We call these Wasserstein geodesic curves, if you will, a notion of a straight line between distributions in the Wasserstein space that now allows us to kind of naturally interpolate between the distributions in the endpoints, smoothly deforming the one until you reach the other. And these ideas actually have a lot of applications in computer vision for shape morphing tasks, for example. Now, the moment that you have geodesics, you immediately get a natural notion of an average of the two distributions at the endpoints, right? Just the midpoint of that geodesic. And you can actually generalize this perspective to talk about averages of larger classes of probability distributions using the notion of Wasserstein barycenters. You can project distributions onto subsets with respect to the Wasserstein metric in a very meaningful way, and keep this in mind because we will go back to these projections later in the talk when we'll start building minimax optimal estimators for our robust distribution estimation task. And in fact, you can even optimize functionals of probability distributions over the Wasserstein space by running gradient flow algorithms. And you can think of an objective that is maybe entropy or some notion of potential or interaction energy. And the idea is that this Wasserstein space effectively behaves almost like a Riemannian manifold. It has a fully differential structure. There's a meaningful notion of a gradient. So you can just follow the negative gradient in order to optimize your objective. And again, these types of gradient flows in Wasserstein space have myriads of applications. If it's for sampling, if it's for non-parametric maximum likelihood estimation, and many other examples as well. So overall, loads of good structure, very rich geometry on a space of distributions that is inherited from the geometry of the underlying space, because all of this is induced by the base metric that sits here in the background. And this is the geometry or discrepancy measure between data sets that I was alluding to, and the figure of merit that I want to adopt as my performance metric for the robust estimation task to come later. Okay, so that's kind of ingredient number one. If there's any questions about the stuff, again, I'm happy to answer.
Question or a comment more. So you are choosing a representation for your data. And assuming that one of these Wasserstein things is the right distance between them, but the true distance could be something else. True manifolds and
yeah, all I'm saying is that, I mean, all I'm asking you to give me in order to build a Wasserstein distance is your notion of a metric between data points. Okay? If you tell me how you measure distances between data points, that I, through this framework, can tell you how to measure distances between piles of data points, which are basically probability distributions.
Well, that may not be the real underlying distance for the representation you're choosing.
Yeah, I mean, if the underlying distance that you chose is wrong, then the Wasserstein metric you will get will not be a good representation of what you're trying to do, of course. Yeah, this is all stitched on top of the base metric. So like, I'm kind of assuming that I have a good one. Yeah, thank you. Any more questions? All right, good. So with that, as I said, ingredient number one, let's start talking about ingredient number two, which is this combined corruption model. It's actually its connection to a very interesting subfield in optimal transport that is called partial optimal transport. And this will actually be our main tool here for modeling, for building estimators, for then devising algorithms and so on and so forth. But let me start from the operational problem. What is this combined corruption model we're looking at? And the idea is the following. So I have my green data set shown here in green, and then comes the adversary that can act on it in two ways. First of all, perform my local perturbation, right? Nudging these green points around with a budget of an average magnitude being at most rho, transitioning from the original green observations to now these blue ones over here. But the adversary is not done at that point because there's a second step of contamination, which is the global one. From these locally corrupted blue points, the adversary can now pick up an epsilon fraction of them and completely replace with arbitrary outliers shown here in red. So by the end of this process, my observation is this red data set that you see over here. And at a high level, the goal would be to somehow retrieve the green data set that we started from. Okay. And in order to do that, let me start kind of giving things names here. So I want to denote by mu, mu prime, and mu tilde the empirical measures corresponding to these clean, locally perturbed, and then also globally perturbed distributions. And perhaps the first thing worth observing here is that the relationship between the clean data and the local perturbation that I'm not showing anymore is exactly described by a Wasserstein-1 perturbation of magnitude at most rho between them, because this is exactly the definition of optimal transport, right? The minimal movement you have to introduce in order to transform one data set into another. And by a similar token, the relationship between this globally perturbed version mu prime and the final, locally perturbed version mu prime and the final globally perturbed distribution mu tilde is exactly described by a total variation perturbation of magnitude epsilon. If you keep in mind the total variation is just half of the L1 norm, this vertical L1 norm distance between your two distributions. And these two, in fact, in terms of their order, can be shown to be interchangeable in the sense that if you start from a clean data distribution and think about all the distributions that you can reach by first Wasserstein perturbing and then total variation perturbing versus first total variation perturbing and then Wasserstein perturbing, you realize you arrive at the exact same set, and therefore I'm thinking of these as being interchangeable in terms of their order. But perhaps even more importantly, as I've mentioned a moment ago, both of these can be described simultaneously by a single partial optimal transport problem denoted here by W1 epsilon. I'll explain what that is in a moment, that directly ties the original clean data distribution with the final contamination mu t. So at this point, maybe I should explain what this W1 epsilon is, because this would be the modeling paradigm that we will be working under. So partial optimal transport. And as you can see,
Can I ask, what's the motivation for taking the average in the local perturbation rather than say the maximum? Is it a mathematical reason or is there a physical reason?
so I mean, yeah, mathematically ties me directly to the Wasserstein distance, so that's more convenient. I guess you can translate between them, and in some sense, I'm giving you more flexibility. I mean, if all you want to do is just take this point very far away, you can, right? If you want to move all of them a little bit, you also can. So in that sense, I'm just allowing you the control over how you want to perturb. That makes sense? All right, good. So partial optimal transport. And I mean, as you can see, it's basically or very similar to the definition before. The only thing that really changes is that the set of couplings is being now replaced with the set of partial couplings that are allowed to first filter out or completely ignore an epsilon fraction of mass from my two marginal distributions. If you will, the epsilon fraction of mass that is hardest to transport, ignore that, and then just solve a regular transportation problem between the rest of the 1 minus epsilon bulk of the mass of the two. And interestingly enough, this partial optimal transport problem can actually be represented in many different equivalent ways that I'll show you next, each of which is useful for different types of analysis, but each of which also kind of reveals a different perspective on this problem, which I think overall is quite illuminating. And the first one here, it's very simple to derive. This is basically a restatement of the definition in some sense. This is what we call the mass removal formulation. And it just explicitly says, well, you're allowed to first pick your best epsilon filtered versions of the marginals, these two submeasures, mu minus and nu minus, and then solve regular optimal transport between them. So that's effectively the definition. I'm just rearranging it a little bit. So, I mean, maybe not very exciting, but interestingly enough, there's also an equivalent mass addition formulation, where now I allow you to add an epsilon fraction of mass to each distribution to get your most favorable super measures mu plus and nu plus and optimally transport them to one another. And to see why this is true, I mean, just imagine sprinkling an epsilon fraction of red mass right over here, over this blue epsilon blob, and doing the same, a little bit of blue mass right over there, over this red epsilon blob, which kind of cancel each other out, no need to transport them anymore, and you're back to the same problem of transporting the bulks. So we can equivalently think about mass addition, and in fact, you can combine them to one another to a third total variation-based formulation. Total variation really corresponds to both adding and removing mass, if you will, but more importantly for me, this directly ties back to the contamination model that I showed you in the previous slide. It really serves as the justification for adopting partial optimal transport as my modeling framework for this combined local and global attack setting. All right. Now, one last thing that I want to say about partial optimal transport, and this will feature in the analysis later on, is that despite the fact that it's obviously not a metric, right, because it's kind of flat within these total variation balls, it is, for lack of a better term, an approximate quasi-metric. And let me explain what I mean by that. So the quasi-metric really corresponds to point A here. Like I said, it's not negative, it nullifies at mu mu, but it is also 0 for various other distributions. It's flat within these total variation balls around of radius epsilon around one of the measures. Symmetry is obvious here. Whereas for the triangle inequality, and this is why I call this an approximate quasi-metric, we have this approximate triangle inequality, which basically requires you to split up this robustness radius into two. And there's actually a very cute geometric argument behind this triangle inequality that I can try quickly showing you guys. And the idea is that, well, in order to go from mu to nu through kappa, as a first step, what I want to try to do is build an epsilon plus delta partial feasible coupling for the mu nu problem, and then proceed with my analysis from there. So I want to build some feasible coupling for this problem that will give me an upper bound on this left-hand side, and hopefully I can then maneuver around in order to get the desired result. Now, to build this coupling between mu and nu, what I want to start from is extracting an optimal partial coupling at the level of epsilon between kappa and mu. And one can show that these types of partial couplings always exist, and I'm showing it in orange, okay? So we have our first epsilon partial coupling. Then, by similar token, extract a delta partial optimal coupling between kappa and nu, shown here in purple, and consider the fraction of mass within kappa that is being moved around by both of these plans, by both of these couplings, and drag it back to the mu world and the nu world in the sense of pre-images, and think about what we've created here, right? Because we've basically created two 1 minus epsilon minus delta filtered versions of mu and nu that are now coupled with one another through their relationship with kappa. And in order to make this rigorous, there is the standard lemma in optimal transport theory. This is called the coupling lemma, that basically gives you a way to stitch together these orange and purple couplings into one coupling that directly connects mu and nu with one another at the level of epsilon plus delta. So this is the feasible coupling that I was looking for. And if you plug it into this problem, you get an upper bound from which you can get the desired result basically by maneuvering triangle inequalities for the Wasserstein distance and for the total variation distance. So from there, it's really easy once you have this construction, which I think is kind of cute. And I mean, this is as much as I need you guys to kind of know about partial optimal transport for what's about to come next. And as I said, this would be our main hammer for dealing with this combined contamination setting that we're interested in. Any questions about any of this stuff?
Can we think of it as a metric, so to the epsilon as a metric on the space of equivalence classes, where each element is like this equivalence class of the epsilon?
It's a good question. I think that the answer, I mean, okay, you don't, it's not a metric because you don't have a valid triangle inequality. But I think that up to this fact, if you're happy with this version, then you can probably think of this as a approximate metric between equivalence classes. Yeah.
And also in the previous slide, you had defined WP of mu minus and nu minus.
Yes.
So like WP does not require its arguments to be like actually.
I mean, not necessarily, right? You can think of transport. I mean, we normalize usually to 1 because it's convenient, to have mass 1 because it's convenient, but you think about so long that the amount of mass is compatible between the two distributions, you can think about transportation.
Yeah.
All right. Yeah, so partial transport is the main tool for dealing with the combined model, but maybe before we get to that, let me say a few words about literature for the kind of existing methods concerning each of these contamination modes separately. And starting from the total variation corruption only case, which just corresponds to outliers, only global contamination, rho here is 0. So I mean, like I said, this goes back to the work of Huber in the late 60s. This is the realm of standard or classical robust statistics with recent kind of resurgence of interest from the TCS community thanks to algorithmic advances. And in fact, in this day and age, we have a standard efficient go-to algorithm that is known to be minimax optimal for filtering out outliers. This is known as the iterative filtering algorithm. And the idea is basically that you filter out an epsilon fraction of mass so as to minimize the largest eigenvalue of your empirical covariance matrix. With the thinking behind it being that, well, if I'm very stretched along a certain direction, this is probably because of outliers. So I want to throw stuff out in order to introduce some shrinkage and therefore get rid of these outliers that we're trying to handle. And I mean, keep iterative filtering in mind because we'll get back to similar ideas later in the talk. Then if you think about the Wasserstein corruption only setting, now I'm only allowed these local nudges, no global outliers. This is well, a topic that received a lot of attention from the adversarial machine learning community, was also explored by the lens of robust distributional robust optimization by the OR community. And more recently, there were actually some folks looking at it from a kind of more standard robust statistics standpoint. But like I said, the main thing to keep in mind is that all of this is fair and square, but the models do not combine. All of these methods, if you try to use them in a setting with both modes of corruptions can be present, do not work either catastrophically or at least become suboptimal as opposed to their minimax optimality before, and therefore some new ideas will be needed, and that's what I would like to start talking about next. Okay, so finally we have all the ingredients to set up this problem. Let's see how it looks like. And I'm starting from my clean distribution mu. Mu belongs to some family G encoding distributional assumptions. And I mean, maybe these are tail bounds, maybe these are moment bounds, and you do have to assume something for robust estimation to be possible, because otherwise nothing is distinguishable, right? You cannot know what's clean, what was a, I mean, you know, you have to have some prior knowledge on how clean distributions look like, and I will put them in this class G over here. And in fact, for the rest of the talk, I will focus on a class of bounded covariance distributions, basically distributions whose variance along every possible direction is not too large, mostly for simplicity. The theory that I'll present extends to other standard tail bounds such as sub-Gaussian or concave, and I'll comment about this later on, but I mean, let's kind of stick with bounded covariance for now. Yes?
Do you assume that you know the covariance, like for the
I know that I assume that I know a bound on the covariance. Yeah, yeah. And I mean, you can have a constant here. I mean, nothing will change. You can have some sigma squared times
But
IT,
you know
but,
that constant.
but I know the constant. Yes, yes. Good. Then comes my adversary, introduces the local and global corruptions at the level of rho and epsilon, produces this mu tilde for me that now I can compactly describe with my partial optimal transport problem, directly connecting it to the mu that we started from at the level of W1 epsilon distance being at most rho. This is what I observed, and based on that, I have to build an estimator of hat that ideally will be minimax optimal in the following sense. So you can see that I'm using my geometry aware, if you will, W1 metric as the performance criteria for my estimator, and basically looking for the best estimator that will be able to perform well even against the worst case choice of a clean distribution under the worst case attack by my adversary. And this is the minimax formulation for our robust estimation question. By the way, you can notice that I'm kind of setting things up here at the population level without sampling. And the problem is already interesting at the population level. In fact, in some sense, it's more interesting at the population level, although you can definitely think of it from a sampling perspective, where the clean distribution first gets sampled, then the adversary contaminates this data set into a corrupted data set. That's what I observed. And my job is to retrieve the clean new population from which the clean samples were generated to begin with. If you think about this finite sample regime, probably you want an expectation over the data over here before the W1, or maybe you want to think about high probability bounds. But I will later say that the finite sample risk effectively decomposes into the robust estimation risk at the population level, this guy, plus a sampling error, right? So really it's the population level problem that is interesting to figure out, and that's what I want to be focusing on. And maybe as one last thing to say here, which is another nice feature of working with this W1 as my loss metric, beyond the fact that it's geometry aware, and it's the fact that whenever you have control in W1, you actually get risk bounds uniformly over a class of Lipschitz 1 loss functions, and these are the types of, this is thanks to W1 duality, by the way, and this is the types of guarantees that we typically care about in statistical learning theory. So another nice byproduct of working with this type of minimax estimation risk, and that's the problem that I want to start thinking about. And let me kind of dive straight into it and show you a highly non-informative version of the main result. Non-informative because it omits the estimator and the algorithm, which are the most kind of interesting bits here, I think, but does provide a full characterization of the robust estimation risk in terms of the two contamination parameters, epsilon and rho, and the dimensionality of the data D, kind of stating that there exists an efficient algorithm that achieves this risk, but I mean, we will see this in a bit, though already at this point, we can discuss two interesting aspects, which is lower bounds, like why is this root d epsilon plus rho risk necessary and unavoidable, and then maybe the performance of some simple benchmarks for this task. And for lower bounds,
You remind me what your risk is again? What's the risk again?
this whole thing, this thing is something. Yeah. Yeah. All right. Yeah, so lower bounds. And lower bounds are actually fairly easy to construct for this problem because we have a very powerful adversary that has a lot of flexibility. So I can maneuver quite a bit when constructing these lower bounds. And I mean, for instance, for this first bit, for this root d epsilon part of the risk that corresponds to the global contamination, right? The total variation perturbation. The idea is really to use the fact that the learner that produces the estimator cannot really distinguish very well between distributions that are epsilon total variation apart. Now, why is that? Well, because even in the very optimistic scenario that somehow the learner can restrict themselves to a set of two distributions, one of which has to be the right one, right? An alpha and a beta, and one of them is the clean distribution. If alpha and beta only differ in epsilon total variation, then the adversary can just flip a fair coin, and as mu tilde return either the alpha with probability half or the beta with probability half, and there's nothing that the learner can do against that except kind of just guessing something in between. And so you have to effectively suffer half of the Wasserstein distance between alpha and beta as your estimation risk. And with this in mind, the question boils down to, well, if you want to show that root d epsilon is necessary, find two distributions that are epsilon total variation apart and are root d epsilon Wasserstein 1 distance apart. And once you frame it like that, it's pretty easy to do. So take your alpha to be just a Dirac at 0, take your beta to be a mixture of this Dirac at 0 with a centered Gaussian with a scaled variance. You can easily check that these two distributions are epsilon total variation apart. Again, the only difference is Gaussian component whose mass is epsilon in total, but when you compute the W1 distance, again, a very simple computation will show that it exactly equals root d epsilon in this case, showing the necessity or the inevitability perhaps of this blue chunk of the risk. And very similar argument applies for the rho. Here you would exploit the fact that the learner cannot really distinguish well between distributions that are rho translation apart. And because the adversary has a rho budget for local contaminations in Wasserstein distance, it can always translate by rho and create the same type of uncertainty. So again, you can think about two distributions that are rho in Wasserstein distance, a valid contamination, and therefore also a rho term has to appear in this risk. Therefore, that's the lower bound, and how to achieve it efficiently we'll see later on. But I mean, that's the first thing that I wanted to say. Yeah, beyond that, like I mentioned, let me kind of just talk about performance of some simple benchmarks for this task. And perhaps the first and simplest thing that you can consider doing as the learner for this task is nothing, right? Just return the contaminated observation. I mean, you see something, return it as your estimator. And funnily enough, if you're in the local corruptions only setting, that's already minimax optimal. And I mean, it's kind of an artifact of the fact that I'm contaminating in Wasserstein and measuring performance in Wasserstein, so things are compatible in this way. So of course, you get this minimax optimality. But the moment that I introduce a little bit of outliers, the do nothing estimator completely breaks down, the risk shoots up to infinity. And there's an easy way to understand that, because if I can contaminate a total variation, I can put a little bit of mass super far away and make my transportation cost explode to infinity, no problem, right? So, I mean, do nothing doesn't really work against outliers, but we have iterative filtering that is minimax optimal against outliers. So maybe if you just combine do nothing with iterative filtering, which is basically iterative filtering, you get an optimal resolution for our robust estimation task. But again, not quite. You get your minimax optimality for outliers only. But the moment that local corruptions are present, you end up picking up this root d factor in front of the rho, which shouldn't really be there as per the lower bounds, meaning that you're paying excessively for high dimensions when you actually shouldn't. And therefore, in the combined model as well, iterative filtering gives you something, but something that doesn't really scale correctly with dimension. And therefore, we do need a new approach. And I'll show you an estimator that is minimax optimal for the combined setting, and therefore also for the two individual ones in particular. And yeah, let me get into that. So towards an efficient estimator, I want to start from an idealized version, an inefficient estimator that will just solve the statistical question. Because first of all, it's easy to explain, relatively easy to explain. And then once we'll have a minimax optimal inefficient estimator, it will at least kind of set the goalposts for us in terms of what to target algorithmically. So let me start from that. And I will use this diagram over here to explain what I'm doing. So I have my clean distribution family G. There's the clean distribution living in it. I don't know what it is, but I know that it belongs to the class. Then comes my adversary, contaminates it in Wasserstein, perturbation rho. Then a total variation perturbation epsilon, which can jointly describe by a partial optimal transport W epsilon, W1 epsilon distance rho at most from one another, again, directly connecting the clean U with the final observation U tilde. And based on this observation U tilde, the estimator that I want to propose is basically project this U tilde back to the clean distribution family G, never mind how to computationally do it for now, with respect to the partial W1 epsilon optimal transport distance. This is actually a classical idea in statistics, in particular in robust statistics. This is called minimum distance estimation. And what it returns is a point in G that is closest to mu tilde in this W1 epsilon partial optimal transport distance with respect to which the projection is performed. And by keeping in mind that, oh, I already know that mu lives in G and is W1 epsilon rho distance apart from mu tilde, the same distance bound has to apply for my mu hat MDE estimator just by virtue of being the closest point, right? And once I'm here, I'm actually in business. Because using my approximate triangle inequality, I can now get a relationship directly between the clean distribution that I'm trying to estimate and this mu hat MD estimator that's trying to retrieve it at the level of W1 2 epsilon, summing up the robustness radii, being upper bounded by 2 rho, again, as per the approximate triangle inequality. And the moment that you have control between the target distribution and the estimator that's trying to get it, you can start actually executing the analysis. And so let's get into that and specifically look at the W1 error between the target and the estimator we've constructed for it, and in fact control it from above by this modulus of continuity over here, which is effectively the W1 radius of the set of distributions within G that are at most W1 to epsilon 2 rho distance apart from one another, which I know contains the two distributions that I actually care about, which are mu and mu hat and E. And the thing is that this modulus of continuity over here is actually pretty nice to analyze, and in particular we can decompose it into the rho that corresponds to the local Wasserstein corruptions plus a certain W1 resilience term of this class G that will take care of the global total variation contaminations, where the resilience of a class is just the worst case resilience of distributions in that class, and the resilience of a distribution, W1 resilience of a distribution, is effectively just by how much can you change it in W1 when all you're allowed to do is perform epsilon deletions. So pick an epsilon fraction of mass, delete it, and renormalize. And turns out that this is kind of the right notion to have in mind in order to treat global total variation corruptions. And at this point, the question really boils down to, okay, so now we need to compute the W1 resilience of the class of interest, which I said is the bounded covariance class. And it's not too hard to do in order to show that root d epsilon is indeed that resilience, showing that the mu hat MD estimator achieves the minimax risk from before, and therefore it is minimax optimal for this robust distribution estimation task. Maybe another thing to mention here is that nowhere in my analysis I actually use the properties of G up to the very last point where we have computed the resilience. So I mean, you can run with the same type of analysis for other classes of clean distributions. Like I mentioned, you can do sub-Gaussian, log concave, bounds on Qt moments. And the only thing that will really change in terms of this bound is that this root epsilon over here will be replaced with some delta that looks like this for these different classes. You still have to adapt the lower bounds in order to show that this is the right thing and you're not too large, but I mean, this can be done and you can obtain minimax optimality at the statistical level for this estimator across these four classes from bounded covariance all the way through sub-Gaussian, log concave, and bounded Qt moments, which is great. You know, if you're a statistician and you just wanted a statistical solution, then we're done. We can go home. We have our optimal minimax estimator. But the moment that you start to think about efficient implementation, you quickly realize that there are some very, very serious obstacles here towards algorithms. I mean, first of all, W1 is not a nice quantity from a computational standpoint. It often has uniqueness issues. It often has non-smoothness issues. So it's just not a nice quantity to compute. And then on top of that, how do you actually perform a projection with respect to a partial version of W1? I mean, highly unclear. And so towards what will hopefully become, spoiler alert, it will, an efficient algorithm for this task, let me replace the inefficient or inconvenient to compute W1 with its much more convenient to compute cousin, which is W2. Okay, so basically what I'm saying, do the same thing, apply a projection estimator, minimum distance estimator, but this time with respect to the W2 partial optimal transport problem. I'm calling this mu check MDE. Here it is over here. And the reason to think about W2, by the way, is because W2 with a quadratic cost, right? So now your cost looks like a metric squared, effectively. And W2 with a quadratic cost almost directly connects to the covariance matrices of the considered distributions and oftentimes gives you access to spectral algorithms. And this is kind of what we'll end up doing through this approach. Thankfully, before all of that, you can still show that this W2 based estimator is still minimax optimal. It achieves the exact same W1 error in terms of what we've seen before of rho plus root d epsilon, although the analysis is much muddier. It's no longer explained cleanly by this diagram over here. You have to introduce various kind of approximating distributions and intermediate steps. In particular, you rely on some comparison lemmas that translate control in regular W1 to control in partial W2. But I mean, honestly, I don't want to get too much into that and rather just take it as, take my word for it for the fact that it's minimax optimal. And let's talk about the algorithmic advantages that we get from switching to this W2 based projection estimate. Okay. And to show you the, yeah, I have, okay. And to show you the algorithm, I want to start by just massaging the objective a little bit. Let's bring it to a slightly more convenient form. So this is the optimization problem I'm trying to solve. I want the argmin of this guy, but I mean, let me just write it as a min for now. And what I want to do is use my equivalent formulations for partial optimal transport in order to replace W2 epsilon here with this minimization problem on the inside, which uses the total variation based equivalent formulation that I showed you before. Okay. Now, once you're here, I basically want to switch the order of these two minima in order to rewrite my objective as now a minimization over a total variation ball of radius epsilon around the contaminated mu tilde observation of an objective that looks like W2, notice, regular W2, not partial W2, so that's already an improvement, W2 between nu, which is my optimization variable, and the full-blown bounded covariance class. And looking at this, by the way, I'm using the standard notion here of the distance between a point and a set. But looking at this, maybe you're thinking, well, I mean, did we gain anything? This looks just as intractable as it did before, but thankfully we have the following tractable approximation lemma using the notion of a positive trace, which is the sum of non-negative eigenvalues of a matrix. And specifically, we can show that the objective squared, again, square doesn't change anything because of monotonicity. We're looking for the argmin. So the W2 objective squared can be sandwiched up to constants between the positive trace of this difference covariance matrix, which is the difference of the observed covariance minus some identity reference. And with this tractable approximation, I can now approximate my objective over here with the positive trace. And this guy actually lends very well for a spectral algorithm, which is what I'll show you next. We call this algorithm the W2 project algorithm. The objective can really be understood as the difference between these two ellipsoids over here, the red representing your empirical or observed covariance, the green is just the reference identity that we're using here. And as a first simple initialization step, let me define this script T over here as just the set of all support points of the contaminated observation. I mean, of course, we will be filtering out points as we go along, but this is what I initialized from. And in terms of the algorithm itself, the first thing that I want to do is identify the positive eigenspace of this difference covariance matrix called the projection to this eigenspace phi. But really keep in mind that what this eigenspace represents is the subspace along which my empirical covariance is the most stretched. So by a similar token to iterative filtering from before, this is probably where you want to introduce some shrinkage. And in order to do that, I'll define a function g that basically projects everything to that subspace and then measures distances between my data points and the projected mean, and filter out a fraction of points have the largest gx values associated to them, again, introducing the shrinkage that we're looking for. And from this point on out, we just keep on iterating from item 1 up until a certain stopping condition is met. And if you really think about what we've done here, well, this is nothing but a multivariate extension of the iterative filtering algorithm, right? It looks at multiple dimensions at once, as opposed to just the one dimension along which there is maximal stretching. And you can indeed show that this is a polytime efficient algorithm that is provably convergent and accurate, and therefore provides us with an implementation of this projection estimator based on the partial W2 epsilon problem. I mean, this is the algorithm with all its glorious details, but hopefully things are clear at this point. And so with that, I'll just go back to my main result and restate it with all the previously omitted details, which is, well, give me any, or pick any distribution from this bounded covariance class, apply a rho epsilon local and global corruption on it, and based on this mu tilde observation, the W2 project algorithm will return an efficient estimator hits the right robust estimation risk. And as I promised you, you can also look at the finite sample version of this result. So now if you observe n contaminated samples, you can still act on them with W2 project and obtain the following risk. And like I mentioned, I mean, the analysis here basically decomposes this finite sample risk into the robust estimation population level risk, which we see over here, and we put up a lot of work in order to be able to characterize, plus this term over here shown in cyan, which is effectively an estimation error. This is the W1 estimation error of the plug-in empirical estimator. We call this the empirical convergence rate under W1 in optimal transport theory. And it's kind of a classical question, again, dating back to the same year, by the way, 1969, work of Dudley, where he showed that this rate is in general given by n to the minus 1 over the maximum of dimension 2. You can never drop below n to the minus half from CLT considerations. But I mean, that's the right rate. And the overall bound we're getting here is in fact near minimax optimal for our task up to the suboptimality of this plugin estimator for estimation under W1, which, by the way, in itself is near minimax optimal up to polylogarithmic factors. So that's the finite sample version of this question. And I mean, in some sense, you know, this is the story of robust distribution estimation with efficient computation subject to formal guarantees. Now, if I have 5 more minutes, I can tell you one more thing. Yeah? Okay, cool. Any questions so far? Yeah.
So in you estimated you know the knowledge of low and epsilon.
Mhm.
So is there any literature that consider to learn the low and epsilon by?
Yeah, it's a very good question. We've thought about it, and I mean, you can relax this notion in different ways. I mean, so there's actually 3 things to know here. One is also like a sigma parameter that for us is 1, but implicitly I'm assuming to know it, which is a variance bound, right? So there's like a sigma, a rho, and an epsilon. And we can actually show that if you just know 2 of the 3, you're still fine. You can usually estimate a third and perform at the right level. But when you only know 1 of the 3, we don't really know how to deal with that. So yeah, it's a good question. You can identify the right row, by the way, by looking at certain statistics and identify an elbow effect. That's another thing that you kind of, you know, you filter and filter and filter, and then you see a real drop in terms of the Wasserstein 1 distance. You can identify the epsilon. But yeah, these are good questions that I don't have full answers for them.
So you had other minimax results.
Yes.
So the same algorithm works in that context, or do you?
If you have variance bounds. So the algorithm, we are looking at adaptations, but the algorithm will still be able to achieve this, right? Because it will effectively be tailored to the variance. So I mean, you do need variance bounds.
Okay, so maybe that question is not fully answered here, but so similar question along those lines is do you know if there is a statistical and computational gap in some of these problems for certain distribution process?
Yeah, great question. I don't know. But I mean,
There could be essentially, if you start with doing W1.
it could be. I mean, so what I can say is that for all of these classes, whether you're sub-Gaussian or rock concave or have bounded youth moments, I mean, you can get variance bounds, right? So you can get like a corresponding result from the W2 project algorithm, but I don't have like an algorithm that is able to exploit sub-Gaussianity per se, right? It's just the fact that, well, sub-Gaussianity gives me variance bounds. And whether there is a statistical computational gap, I mean, my gut feeling is no, but I don't, I don't know. Yes.
In the case where the covariance is unbounded, like the distribution that is like the covariance, you don't have a second mode. I assume in those settings, even the simplest cases, there is no.
I mean, heavy tail estimation is within the realm of robust estimation, right? I mean, when you deal with outliers, effectively, you are dealing with heavy tails.
Yes.
So yeah, I mean, again, this assumes a variance bound, right? But I think that within the robust statistics literature, you would have also approaches for dealing with heavy tail distribution.
But I guess the variance bound is on the set G.
Sure, yeah.
I guess the question is perhaps G is heavy tail. Then.
Oh, so for
Yeah.
like for the mutil, you mean? I mean,
Yeah, so the class,
No, not the mutal, but the G itself is heavy tail. I mean, your true distribution is from a heavy tail as
Yeah.
opposed to the mutal converting it to heavy tail, which
Yeah.
is allowed in your
yeah,
formulation, but.
yeah. I'm not sure. It's a interesting question.
Can you define W2 without second mode?
W2 has, so any WP assumes a finite peak moment. So W2 needs, so I mean, this approach is kind of very reliant on the fact that we have a variance belt. What to do with heavy-tailed? I mean, and all my other clean classes have even lighter tails, if you will,
Yeah.
right? Yeah. So how to deal with heavy-tailed clean populations? Yeah. Interesting.
Even the iterative filtering, that algorithm
Also assumes covariance. Yeah, I agree. Yeah. All right. There are results for mean estimation for heavy-tailed distribution, robust mean estimation. Yeah, but I don't know if you can estimate. I mean, I'm not sure what's known about estimating the full distribution. Right. So one last thing that I want to say is that if you care about efficient implementations and like formal guarantees for these algorithms, then W2 Project is the way to go. But if you're a practitioner that just wants something that works and works at a scale and can handle high-dimensional data and large data sets, then actually there's a very cool heuristic implementation here as well, based on neural networks without guarantees, but one that works very well. And let me quickly tell you about that. And that actually relies on kind of a new duality theory for partial optimal transport that we have devised. And I'm showing you the version that is just specifically stated for W1 epsilon. This is a more general result than this. And in particular, what it says is the W1 epsilon can now be represented in the following dual form as a supraroom over Lipschitz 1 function of this objective, where for those of you who are familiar, the first part of this objective is kind of the regular W1 duality. This is the standard Kantorovich-Rubinstein dual, but in the partial optimal transport problem, you see that there is this -2 epsilon subnorm regularizer, if you will, that emerges there that in some sense kind of cuts off the dual potential and takes care of the outliers. Now the proof, I don't think I have time to go through this, but let's just leave it at that. And instead use this result in order to talk about this heuristic neural implementation, and notably an implementation of the idealized W1 epsilon projection estimator that we couldn't compute before. Okay, and here's the idea. So again, this is my optimization problem. I want the argument, but I'm running this as a minimum. And first and foremost, well, I don't have any way to optimize over all possible probability measures new over here. So as a first order approximation, let me approximate this new with a neural network generative model, basically taking some simple latent variable. Maybe this is a Gaussian, maybe this is uniform on a ball or something like this, and pushing it through a fancy deep neural network, G theta, a generator network, which reduces my optimization now to just the parameters of this neural network, and the new theta distribution I have in mind is the one that sits at the output of this generator. Okay. Now into this, plug my dual form from the previous slide, and again say, well, I have no way to optimize over all possible Lipschitz functions, so let's approximate them by a second neural network, discriminator network, if you will, denoted Fp, phi being the parameters, again reducing this optimization problem to being a maximization over the parameters of the second network. And now observe that what we have arrived at here looks a lot like the minimax training objective for the Wasserstein generative adversarial network, the WGAN, that by the way, for many years was kind of the state-of-the-art generative model up until it was made obsolete by diffusion models. But the point is for us is that there are highly efficient, parallelized, and optimized codes for implementing WGANs, and the only difference between my objective and the standard WGAN is once again the appearance of this -2 epsilon subnorm regularizer, which can be accounted for by changing a single line of code. So funnily enough, you can grab your favorite implementation of a WGAN, introduce one more line of code, and get a robustified version of your WGAN, and it actually works very well on data. So I can show you some experiments. We're basically training here a GAN without this robustness penalty and a WGAN with the robustness penalty on contaminated data sets that maybe mix MNIST digits with noise, or celeb A images with MNIST digits or something like that. And you can see that when I learn without my penalty, I end up learning the corrupted distribution and generating samples that are also from the undesirable kind of modes that correspond to corruptions, whereas with the penalty, the model is able to extract the clean distribution in the background, overlook these corruptions, and get me back my clean mu that I want. So, I mean, it's kind of nice. And like I said, I mean, we don't have guarantees for this, but this can actually work at a very large scale, although these experiments are not at that scale per se. So yeah, with that, let me just quickly summarize what we've discussed. We've talked about this robust distribution estimation problem with local and global corruptions, with this W1 metric as the performance criteria. We've identified partial OT as kind of being compatible with this framework, so we used it as kind of a main tool to, first of all, devise these two minimax optimal estimators based on W1 partial and W2 partial optimal transport problems. For the latter, we had an efficient implementation in the form of this W2 project spectral algorithm, thanks to a tractable approximation of the projection or optimization objective in this case, whereas for the formal, we have this neural compute implementation building on the duality theory plus parametrization by neural networks. So yeah, I mean, these are the papers that I talked about. Check them out if you want to see any more of the details. And with that, guys, thank you for listening and for the wonderful questions. This was really fun, and I'm happy to answer anything else that you have in mind. Yes.
Yeah, so, these two distributions that you talked about, the two marginals, are these like, the source distribution and the target distributions, or like how do these relate to the regenerative model bubble?
So where specifically?
So you're talking about like a coupling between two distributions.
In like in general optimal transfer framework? I mean, these are any two distributions that you care about.
Oh, so you're not doing like a model sort of thing where you start with one distribution and you map it to.
No. Optimal transport is just a question of comparing between probability distributions. You can ask it in a vacuum without any application in mind. Right. Now, the way that we've used optimal transport is a estimation loss that compares what I'm trying to get, which is the clean distribution in the background, and what I'm building to try and obtain it, which is an estimator. So our optimal transport distances were between mu and mu hat, if you will, mu being the clean and mu hat being my estimator based on the mu tilde contamination that I observed. There's no, I mean, I didn't have any diffusion models at this time.
Okay, thank you.
For the partial W1 distance, how do we construct which 1 minus epsilon term is going to be transferred and which is not going to? How is that?
So you optimize, right? Like if I go back to the definition, you don't, I mean, you want to pick the submeasures post epsilon filtering that are, it might take me a minute, that are cheapest to transport. So you pick the ones that have the least transportation cost between them. And I mean, in this picture that I've been showing, almost there. Right, in these pictures that I've been showing, right, you can see here. I pick them by optimizing over them. I want to pick the mu minus and the nu minus that bring this transportation cost to be the lowest that it can be. So effectively, you want to filter out the parts that are somehow furthest away from one another in the transportation sense. And I mean, in this picture, this would actually be these two small blobs on the left and right hand sides. Yes.
So when the distribution is essentially in a low dimensional space.
Good question.
Like
Yeah.
intrinsic dimension is lower. The lower bound probably instead of square root of d, you would get square root of.
Yeah. So this is something that in the paper, you will find that we actually don't analyze under W1, but rather under a sliced W1 distance. So I mean, there are versions of optimal transport distances that first project to a low dimensional space and then perform the comparison over that space. And I mean, which low dimensional space in particular, again, you pick the one that makes the distance on that space the largest. So you supermise over Stiefel manifold, if you will, a optimal transport problem between the projected versions of your distributions. Now, if you adopt this this sliced Wasserstein distance as your performance metric, then all this theory can be adapted to the underlying dimension of the data.
So in the algorithm itself, there is one additional step of projecting before filtering. Is that?
No, the algorithm would be the same. The performance criteria will be different. That's the only. The algorithm will be the same. The performance criteria will be instead of like W1 and W1K, right? Where K corresponds to the projection dimension. And then root K will, instead of root D, would appear in your bound.
Ask the question though, even MNIST images are already D equals about 800, that's already.
Yeah. So you can adapt, I mean, I just didn't have time, honestly, to get into it, but you can adapt all of this with a little bit of technical overhead to see the underlying dimension, the intrinsic dimension.
So in fact, Celebbe images are not the same as MNIST images, so did you sample them to make them match?
Yeah. Exactly.
With, probably with the MNIST dimension, the smaller dimension?
Yes.
Oh, yeah, okay.
Yeah, that's why the Celebbe images look horrible, and you
Yeah,
cannot
okay.
really even tell that these are humans, but okay. Yeah. But this was like, the experiment that I showed was more like a proof of concept. We didn't try to do it at a large scale, but my comment is based off the fact that Wasserstein GANs work at a large scale, so you can just regularize them to robustify this way.
So your adversary is able to change your initial distribution however it wants, as long as you are in this Wasserstein plus the TV ball. would it be interesting to think of a setting where your adversary is a little bit weaker than that, like some kind of average case analysis instead of a worst case analysis, then you can maybe improve the lower bounds.
I mean, it's interesting. So what weaker adversary you have in mind?
In the sense that like in real life, maybe you have certain noises instead of like an adversary picking however it wants to move the data set. You move it under a certain.
Okay, I can say on one hand, in principle, you want to assume as less as possible about adversaries because you want to be prepared for the worst case and you don't know what the adversary is actually going to be or whatever restrictions may apply on them, what they are a priori when you're building your estimator. So I think kind of the first question to have in mind is to try and treat a setting with a strong adversary. Now, whether there are interesting relaxations of the setting, possibly so. I guess one would have to kind of figure out what sits in between our contamination model and yeah, or kind of what is exactly weaker. I don't have a concrete idea for that, but like yeah, if you have one, I'm happy to. Oh yes, sorry. Let's evacuate.
Probably, yeah. Wanting to comment.
So I should stop the Zoom call?
There is, but